All right, so we had an entire unit on vectors. When was that? We got one. Was it?
It was over spring break.
Yeah, I was gonna say it had to been around. It had to been chapter 6 around spring break. Okay. Um, everything that we did with vectors in 2 dimensions, we are now going to do in 3 dimensions. So we just need a couple reminders. There will only be maybe one thing that will be new to you today. Everything else is just a reminder of what we did in 2D and how do we do it in 3D. Okay? So, the first, we have an ordered triple with the chevrons. That means we have a vector, okay? Now you can just watch me graph this. You don't need to graph it. Okay? So, negative 1, 2, 4. We have negative 1, 2, 1, 2, 3, 4. Okay? That would be the coordinate, negative 1, 2, 4. So if we draw the vector, we have to map out the coordinate and then draw the vector from standard position. Okay? Now, what if I wanted the vector PQ in standard position if you knew that P was the coordinate 1, 2, 3, and Q was the coordinate negative 2, 0, 5. How would we get the vector PQ? Jackson?
Take Q and subtract P.
Okay. Remember, I emphasized this quite a bit back in chapter 6. We have to take the terminal point and subtract the initial point. What? So Gabe, the vector PQ would be what? Negative 3, negative 2, 2. Is Gabe Fish correct? If we take terminal minus initial, would we get negative 3, negative 2, 2? Yes? Okay. So if we were to map that out, negative 3, negative 2, and then up 2 would be that coordinate. So in standard position, that would be our vector. So all that we've done is we plotted the point and then we just draw the vector from the origin to the coordinate. Okay. All right. Do you remember when we worked with the vector I and the vector j? Okay. What were those vectors?
I was like 1 unit in the x direction, and j was 1 unit in the y direction.
Okay. I was 1 unit in the x direction, j was 1 unit in the y direction. We're probably going to need one for the z direction. What do you think we should call it? It is, I know, Adrian. It is called K though. Okay, so vector I is now the vector 1, 0, 0, because we're now in 3 dimensions. Vector J is now the vector 0, 1, 0. And now we have vector K, 0, 0, 1. Okay, so they're the unit vectors in the specific directions. Okay, so as you recall from chapter 6, there are 2 different ways to represent a vector. You can write them in that standard form with the chevrons, or you can write it as a linear combination of the unit vectors, like this. 3I minus 5J plus 2K. That means the same thing as the vectors 3, negative 5, 2. Okay, when we introduced vectors, I showed a clip of the villain vector. Okay, and we talked about how the definition of a vector is something that has direction and magnitude, right? What is the meaning of magnitude? It is the length of the vector. Okay? I'll remind you that if we're talking about the vector v, then we say the magnitude is this. It's like the double absolute value bars. Okay? Connor, do you remember how we found the magnitude?
I want to say we used, it was cosine, no, not, no. Can I say it?
What is one of our tricks to finding length in a plane? What geometric concept?
The Pythagorean theorem.
The Pythagorean theorem.
Oh, okay. Yeah. Take the a squared plus b squared plus c squared.
Okay. So if we turn it to our vectors, we take the x component squared plus the y component squared. Okay? So this is if vector v is v1, v2. Okay? In 3 dimensions, if our vector is v1, v2, v3 to represent our 3 different components, then what's going to change about the magnitude?
3 squared.
We just have that 3rd dimension. Okay, so it's still following kind of that same concept as when we looked at the distance formula in 3 dimensions. Okay, where we really just have to add in that 3rd dimension to the same formula. So vector v for this example is negative 1, 2, 2. You find that I'm going to give you 60 seconds to write down what you think the work is for the magnitude and the answer, and then we'll compare. Gabe. Gabe has an answer of 3. Does anybody agree with that? Yeah? We take the square root of negative 1 squared plus 2 squared plus 2 squared, we get the square root of 9. Okay? And so our magnitude is 3. Exciting stuff. Okay. I would like you to write down these two vectors. Vector u is the vector 1, negative 2, 3. And vector v is the vector 0, 5, negative 2. Is that the same from before? Never mind. Just kidding. Fill in for me. Okay? You and your pod need to work together to find me u minus v and 5v plus 2. Plus 2u. Amanda, what did you get for the first one?
Did you multiply that?
Oh shoot. Oh shoot. I did it by it was
Okay, I tricked a couple of you because this is 5v plus 2u. Up here, u is written before v. So some of you just like went right in order, right? uv, that's how it should go all the time. Be careful, okay? Because is this an overly difficult concept? It is, okay. Maybe reading is the issue. Okay, so just pay attention to the details. Okay, so if you take 5v plus 2u, Kelsey, what do you get?
I got 221 negative 4.
221 negative 4. All right. Next concept we need to brush up on. A unit vector. What is a unit vector? Dave knows? Vector with magnitude 1. Okay. So, something that we did back in chapter 6 is we took a vector and forced it to be a unit vector. Does anybody remember that formula? And the denominator was the magnitude. Let me piece the rest of it together.
Was it like the x above the magnitude? Is it like the x component of the magnitude and the y component of the magnitude?
Oh.
Yeah, pretty much. Basically, we take 1 over the magnitude and we multiply it to each component of the vector, which is what you described to me. I'm just making it a little bit more simple for you. Okay? So we take 1 over the magnitude and we multiply it to each component of V. So if we go back to our vector, -1, 2, 2, we decided that its magnitude was 3, correct? So if we wanted a unit vector in the same direction, then we would take 1/3 and multiply it to -1, 2, 2. So our unit vector would be -1/3, 2/3, 2/3. Now, some of this should be fairly fresh because we just took our final, right? Okay. All right. One of the nice concepts, I always like the dot product. I think it's pretty great. If we're taking the dot product, it is one of 2 ways to multiply vectors. You don't know the other one.
Will we be learning?
Tomorrow.
Oh,
So let's take vector V and multiply it to vector W. When we do the dot product, and explain to me how we do the dot product.
So you multiply V1 and W1, and then the same with C3 and V2 putting them together.
Great. So if we have 3-dimensional vectors, how do you think it's going to change? Okay, so it's going to look the same except we're going to tack on V3 times W3. So we're going to multiply the X components, multiply the Y components, now multiply the Z components and add those 3 numbers together. So these are the 2 vectors we are going to use. Vector V is -1, 2, 2. Vector W is 3, 2, -1. And if we want the dot product, VW, then we're going to take -1 times 3, add it to 2 times 2, and then add it to 2 times -1. So our dot product would be what? -1? You guys are all so quiet. Speak up. This is gotta be one of the only classes you're actually taking notes in because you're studying for finals in your other ones, right? No? Not so much? Okay. The angle between 2 vectors. I think some of us were trying to think of this formula earlier instead of a different formula. The angle between 2 vectors. It involves which trigonometric function. Cosine. Darby, do you remember the rest? Hannah remembers the rest?
Oh.
There it is. She's referencing her notes.
She's working smart over there.
Okay, this is how we find the angle between two vectors. Now remember, your calculator is only going to spit out a number between 0 and 180. So this is always going to find the closest angle between the two vectors. Okay? So if I have vector u as 1, 0, 2, and vector v as 3, 1, 0, and I ask you to find the angle between these two vectors, we need three things. We need the magnitude of each, and we need the magnitudes of each. So I guess I just said that. We need the magnitudes of each, and we need the dot product. So how about this? Pod 1 and 4, find me the magnitude of u. Pod 2, find me the magnitude of v. And pods 3 and 5, find me the dot product. We'll break it up.
Do you remember what I told you?
Whatever, we don't know what pod number we are.
You're pod 2. So you have the magnitude of u, correct? No, v. Well, what's the magnitude of u? What's the magnitude of v? And what's the dot product? 3? Okay. So if we want the angle in between the two vectors, we're going to say the cosine of theta equals 3 over radical 5 times radical 10. Please be careful when you're using your calculator. When you punch in inverse cosine of 3 divided by radical 5 radical 10, there is a product in your denominator, which means you need to either take the product before you type it in, or you need to put it in parentheses, okay? So you can either say the inverse cosine of 3 over radical 50, or you can say 3 over parentheses radical 5 times radical 10. If you don't do that, order of operations will not be correct and you'll get an error. Make sure that you are in degrees. Since we have a positive fraction, you should get an acute angle. Negative cosine would give us an obtuse angle. So what do we got? 4.9 degrees. Now, we do have some special things that happen. If this is a 90-degree angle, what special calculation happens? What's the cosine of 90 degrees? 0. Okay. So do you remember how when we talked about if the dot product is 0, what does that mean about our angles? There's a 90-degree angle. Remember we call them orthogonal. Okay. If that dot product is 0, we have orthogonal vectors. Now I thought we could get done before lunch, but we have one more thing to talk about. And let me lead into that, and then we'll do the math after lunch, okay? Now, if this angle between two vectors were to be 0 degrees or 180 degrees, what would we call our vectors? Parallel. If they're going in the same or exact opposite directions, we would have parallel vectors, okay? Now, if we actually calculate the angle, that is one way of telling that we have parallel vectors. But there is actually one more way to determine we have parallel vectors without having to do this math. Does anybody remember how to visually look at a vector and to see if it's parallel? Say it. If they're like proportional. Like, give me an example.
All right.
Ish. Give me an example.
If you like 10, 5, 1, and then 20, 10.
Okay. So if you have two vectors that are scalar multiples of each other, then we know that they're parallel without actually having to do the calculations. Okay, it could even be this, right? If they're scalar multiples, we know that we have parallel vectors. After lunch, we'll talk about why that'll be important. So before we went to lunch, we determined that if two vectors differ by a scalar, like a multiple scalar, then they are parallel. So Dave gave us this example. I tweaked it for some negatives, okay? But if you could multiply one vector by a scalar to get to another, then they are parallel. Okay? What we need to determine if I give you 3 points, I want to know if they're collinear. Okay? So based on the conversation we just had, how do you think we can determine with vectors if 3 points are collinear? Darby.
Well, you could make every point a vector going like from the origin to the point, and then you could take all those vectors and see if they're parallel, and if they are, then they're collinear.
Okay. Okay, so you're saying make the point a vector? Okay.
Like a vector from like the origin to.
So if this was the origin and these were my 3 collinear points, those would be the vectors. You are on the right track. Justin.
You could make 3 different vectors from those points. You could make vector PQ, QR, and PR, and if those vectors were parallel,
Okay, so if we had P, Q, and R, what should be true about vector PQ and vector QR if we have collinear points? They should be parallel, right? Even if your vectors look like this. If we take 3 points and create even just 2 vectors that share a point, if those vectors are parallel, then they have to be collinear. If those vectors are not parallel, then we can't draw a line through all 3 points. Okay. So it does not matter. Okay. So I'm going to just go ahead and write up here. Okay, I know Jackson said we can make 3 vectors, and we can, but we only need to actually look at 2 of them. And it doesn't matter which 2 you look at, okay? If you have this vector and this vector, okay, those 2 are parallel, we're still going to have 1, 2, 3 collinear points. Okay? So it doesn't matter which vectors you choose in which order, no matter what, if those points are collinear, you will get parallel vectors. Okay? So here are our 3 points, P, Q, and R. Tannen, what's one vector you would like to look at?
I like the way Q.
Okay, Q and what? So let's find the vector QR. If we were to find the vector QR, we need to take terminal minus initial. So 0 minus -4, 6 minus 8, and 7 minus 1.
I think that's first. Oh, I don't know.
Okay. There's a vector QR. Nicole, what other vector would you like? PR. Remember, there is no wrong answer. So the vector PR, terminal minus initial, we have 0 minus -2, 6 minus 7, and 7 minus 4. What's true about these two vectors? Okay, they are scalar multiples of each other. Okay, so well, we can take PR, multiply it by 3, excuse me, not 3. We can multiply it by 2 to get QR, right? Which means these are scalar multiples, all right? So since we can write QR as a scalar multiple of PR, that means they are parallel. And P, Q, and R are collinear. Okay. Why didn't we just find the equation of a line to see if all 3 of those points were on a line? Okay, we're talking about 3 dimensions. All right, with slope we have rise over run. With 3 dimensions we have rise, run, and I don't even know what you would want to call the third. All right, but looking at vectors is basically thinking about slope. Okay, we're going x, y, z the same amount proportionally from one point to another. So it's our way of looking at slope without actually calculating. All right, the rest of the class is yours to work on homework. Okay. All of this will appear on next week's test. So make sure you do all of the problems start to finish, especially this one since it's like the only new kind of problem that we have seen. All right, definitely one you want to practice.